Imagine you're holding a basketball at the top of a skyscraper. You let go. It falls smoothly, passing through every possible height on the way down. Now imagine the same drop, but the ball is gone. It's a single neutron, and the fall does something that feels illegal. It does not get to be at every height. There are forbidden heights, not because of magnets, not because of electricity, not because of some hidden trap, only because of gravity. For the first time, we can watch a particle behave as if Earth's gravity is not a smooth ramp, but a set of allowed levels, a staircase. And the shocking part is not that quantum mechanics is weird. The shocking part is that gravity, the weakest force you experience every day, is the thing drawing the lines. To understand why this is so extreme, you need one harsh fact. Gravity is unbelievably weak compared to electromagnetism. The electric force between two protons is about 10 to the 36 times stronger than their gravitational attraction, a 1 followed by 36 zeros. So in almost every lab experiment, gravity is a background whisper. Electric and magnetic effects dominate everything. That is why quantum gravity is so hard to touch experimentally. Not because quantum physics is rare, but because gravity usually cannot shape anything cleanly before other forces drown it out. So physicists chose a protagonist that is as quiet as possible in the electromagnetic world, a neutron. A neutron has mass, so gravity pulls on it, but it has no net electric charge, so it is not constantly being yanked around by stray electric fields the way charged particles are. There is still a problem. A normal neutron is fast. Too fast. If it's moving at hundreds or thousands of meters per second, it is gone before Earth's gravity can do anything interesting on micrometer scales. So the experiment starts by doing something that sounds absurd. They slow neutrons down until they crawl. Ultra-cold neutrons. These are neutrons moving at just a few meters per second, under roughly 8 meters per second, under about 26 feet per second. Jogging speed. Slow enough that gravity has time to shape their vertical motion in a measurable way. And now comes the part most people find hardest to believe, even though it is real and well established in neutron physics. At these ultra-low energies, neutrons can bounce off certain materials like a rubber ball bounces off a wall, not because of electric charge, because of a quantum interaction between the neutron and atomic nuclei in the solid, which makes the surface behave like a potential barrier for very slow neutrons. If the neutron is slow enough, it cannot enter the material, so it reflects. So now you build a trap that uses almost nothing, a perfectly polished horizontal mirror on the bottom, Earth's gravity pulling downward. The mirror acting as a hard boundary the neutron cannot penetrate. The neutron is trapped vertically between gravity and the mirror. This setup has a name, a quantum bouncer, and this is where the staircase appears. In the early 2000s, researchers built a deceptively simple test. They sent a beam of ultra-cold neutrons over an ultra-polished mirror. Then they placed a ceiling above it, not a solid roof, but a rough absorber that would swallow any neutron that touched it. Then they varied the gap between mirror and absorber and counted how many neutrons made it through. If the neutron were a classical particle, the result would be boring. As you make the gap smaller, fewer neutrons get through, smoothly, continuously. But that is not what happened. At certain gap heights, the transmission collapses almost to nothing. Then, as the ceiling is raised, neutrons reappear not gradually, but in sharp turn-ons, step by step. A staircase. Because the neutron is not allowed to have arbitrary vertical energy, it can only occupy discrete gravitational bound states. Here is the clean intuition. In quantum mechanics, bound systems have quantized energies. Electrons and atoms have discrete levels. A particle in a box has discrete modes. This neutron above a mirror is the same idea, except the potential is just mgz, gravity increasing with height, and the mirror is effectively an impenetrable wall at zero height. Solve that quantum problem, and you get allowed stationary states. Each state has a characteristic height scale. The lowest one sits around a few tens of micrometers above the mirror, on the order of about 13 micrometers for the first state, then around 24 micrometers, then around 32 micrometers, and so on. To get a gut level feel for that, 13 micrometers is about 5/10,000ths of an inch. So when the gap is too small to support even the lowest state, the neutron cannot form a stable vertical quantum state in the slit and transmission drops drastically. When the gap becomes tall enough to accommodate the first state, transmission turns on. When the gap becomes tall enough for the next state, transmission increases again. That is the staircase. The neutron is not teleporting. It is not jumping through space in the way science fiction suggests. What you are seeing is mode selection. Only certain wave patterns are allowed between gravity and the mirror, and the absorber kills any neutron whose wave function reaches too high. When you scan the gap height, you are turning allowed quantum states on and off. This is what makes the result so clean. The vertical structure is being set primarily by gravity, not by electromagnetism. Now look at the energy scale. These gravitational states are unbelievably tiny in energy. In the pico-electron-volt range, 10 to the minus 12 electron volts. A visible light photon is a few electron volts. These states are roughly 1 trillion times smaller, and yet they can be resolved. That requires extreme control. The mirror must be astonishingly flat and clean. Vibrations must be suppressed. The geometry must be stable at micrometer scales. The neutron beam must be slow and well characterized, because any stray magnetic gradient, surface roughness, or mechanical jitter can smear the delicate quantum states. And still, the staircase appears. That tells you this is not an artifact. It is a real, robust quantum phenomenon. So why does this matter beyond being a beautiful demonstration? Because it creates a rare experimental regime. A quantum system whose binding potential is gravitational, not gravity in the Planck scale, graviton sense. This does not prove that gravity itself is quantized as a field, but it is a quantum object living in a gravitational potential that you can control and measure. That makes it a precision tool. And here's where it connects, carefully and honestly, to the dark universe. We know the universe's expansion is accelerating. We label the cause dark energy, but we do not know what it is. Some models propose new scalar fields that could act like an additional force, but hide in dense environments by changing their effective properties. Chameleon fields and symmetron fields are examples people study. If an extra short-range force exists near matter, it would slightly modify the effective potential above the mirror, on top of MGZ. And if the potential changes, the energy levels change. That means the positions of those quantum steps shift. So by measuring these gravitational levels more precisely, you can test whether there is any extra interaction acting on the neutron besides standard gravity. This is what makes the whole thing more than a stunt. It is a laboratory sensor for new forces that could otherwise be extremely hard to detect. And modern versions of these experiments do not only count neutrons through a slit, they use resonance techniques to drive transitions between gravitational states and measure the energy splittings with much higher precision. The goal is simple. Ask nature a yes or no question. Do these levels match the predictions of a neutron in Earth's gravitational potential above a mirror, or is there a tiny, consistent deviation that points to something extra? Now zoom back out. You drop your keys. You watch a ball fall. It looks smooth, continuous, obvious. But that smoothness is not a fundamental rule. It is what you see when objects are big and environments are noisy. Underneath, if you strip away everything except a single particle, a mirror, and gravity, the universe draws a staircase. Not because we built it, because it was always there. And the more precisely we measure those steps, the more brutally we test a possibility that physics still cannot close. That even in the most familiar force in your life, gravity, there may be an extra layer of reality hiding just out of reach.